So this lesson is all about sketching polynomial functions. Now, we already sort of did this before, I think in 5.1 or 5.2. But in that lesson, we sort of did the painstaking method of making an XY table, plotting in points. It sometimes wasn't too accurate, and ultimately it gave us a basic shape, but today's goal is to see if we can't make that shape a little bit more precise. Now before we do that, let's recall something from 5.2. From 5.2, we discussed this thing called end behavior. And I think in that lesson, we sort of made a little matrix, little table here. And the idea is that end behavior is dependent on two things. It's dependent on the degree of the polynomial and the leading coefficient. What are the conditions, or what's so important about the degree? Whether or not the degree is even or odd. And what's so important about the leading coefficient is whether it's positive or negative. And the idea was that if you have a polynomial function with even degree and positive leading coefficients, we know they'll go up on either end. We really don't know what happens in the middle, right? How are they connected? Is it a simple loop? Is it a curvy thing? We do not know what happens in the middle, but the very ends, we know this is the case. If the degree is odd and the leading coefficient is positive, we know it's going to go down to the left and up and to the right. Again, what happens in the middle, we have no idea. If the degree is even, leading coefficient negative, exact opposite. And then odd degree, negative leading coefficient, the exact opposite. And there were special notation for writing end behavior. So if I had a polynomial with even degree and positive leading coefficient, like in the top left corner situation, I can see that the function f of x goes up towards positive infinity as I go to the left, as x approaches negative infinity. And f of x goes up as the graph goes to the right. So let's go ahead and take a few moments and fill the end behaviors. Now we did this in 5.2, so if you have no idea what these arrow notations mean, go ahead and check out 5.2 for a quick refresher, or just ask me in class. So this gives us an idea of where the graph should go at the very, very ends. Right? Today we'll be analyzing what happens in the middle of the function. How can I actually figure out where those ups and downs are? I've been using very informal terms, ups and downs. But in the world of polynomial functions, those things are called turning points. Right? So in a polynomial function, or the graph of polynomial functions, turning points, these guys, they are the peaks and troughs of polynomial graphs, or graphs of polynomials. So if I just drew a random squiggle polynomial function here, say something like that, these guys here are the peaks, these guys here are the troughs, right? The max and mins, the ups and downs, tops and bottoms. Now the term local maximum is simply the y value of any peak. Conversely, the local minimum is the y value of any trough. The word local simply means around that area, because of course we know, in my quick squiggle here, these guys are not maximums, because these arrowheads means that the graph will go forever, forever, forever up. So technically there is no maximum. But if I only just look in this area here, clearly we can see that the blue point there is the highest point of the mountain. So that would be a local maximum. In addition to knowing end behavior, in order to sketch pretty decent, accurate pictures, we have to remember a couple of true statements. Recall, the following statements are equivalent. For any polynomial, y equals f of x. Statement number one. Actually, I'll use a bullet point because there is no particular order to these statements. X equals some number else you see is a 0 of f of x. What does that mean? That means x minus that number, x minus c, is a factor of f of x. Well, what does a 0 factor mean? That single number, x equals c, is a solution to f of x equals 0. That's the definition of a 0. It's any number that makes the whole equation equal to 0. And probably more importantly, for our purposes in terms of sketching, x equals c is an x-intercept. Of course, this only works if they're real numbers. So this is probably the more important idea here, right here. If we can solve an equation, and if our answers are real numbers, then I can guarantee myself that they are going to be x-intercepts. So let's just do a quick exercise here. Suppose I ask you to find the x-intercepts of f of x equals x plus 5, x minus 1 cubed, x plus 3 squared. Right. And I said quick exercise because I made it easy for everyone. It's already in factored form. So to find the x-intercepts, you just set the equation equal to 0. So normally this would be a hard question because there's a lot of x's, a lot of exponents. But since I already gave it to you in factored form, we just go straight to the zero product property. If it's in factored form, you just set each factor separately. Equal to 0. So you get x equals negative 5 here as one x-intercept. Now, cubing something, let's in this middle guy here, cubing something just means you write it out 3 times. Same thing with the square. Square just means you write it out 2 times. So in the middle case here, we get x equals 1 3 times. And in the right case here, we get x equals negative 3 2 times. Now, the idea of an answer coming up more than one time is called multiplicity. So on the very, very far left here, the answer of x equals -5, it only came up once. So I would say it has a multiplicity of 1. The answer of x equals 1 showed up 3 times. So I would say it has a multiplicity of 3. And the answer of x equals -3 showed up 2 times, so I would say it has a multiplicity of 2. Right. What do these multiplicities do to the x-intercepts? Well, the easiest way to see that is just to simply graph it. So, I have a computer here, so I can go ahead and use Desmos. If you have a graphing calculator, I would use a graphing calculator. If not, just go ahead and take a look at what the picture looks like and just draw a hand sketch it in your notes here. So I already did it beforehand. So let's graph x plus 5 times x minus 1 cubed times x plus 3 squared. And you get something like this, right? So I'll go ahead and crop this into our notes here. And again, just do a quick shape. It doesn't have to be picture perfect in your notes here. There we go. So this is what the graph should look like. And again, if I were to hand draw this in my notes, I see have as an x-intercept at -5, has an x-intercept at -3, has an x-intercept at 1. I'd probably draw something like, it doesn't have to be super duper perfect. Something like that, right? But what I really am interested in is what's happening at the x-intercepts. So let me highlight the x-intercepts again, -5, -3, and 1. Right? So we have here two behaviors or two things that can happen at an x-intercept. And actually, I'm going to highlight them in different colors here. It looks like at x-intercepts, the graph can just cut through the x-axis, highlighted in yellow here. But notice at x equals -3, highlighted in pink there, it sort of touches and then gets bounced off. Well, what happens or what determines whether or not an x-intercept cuts through or bounces off is this idea of multiplicity. Notice that it cuts through the graph at x equals -5 and x equals 1. These guys here. Notice it bounces off at the x-intercept of -3. This guy right here. So the only thing that separates the multiplicities of the yellow to the multiplicities of the pink is even or oddness. And that's sort of like the big idea when it comes to what happens at the x-intercepts of polynomial functions. Right? So let x equals c be a real zero, aka x-intercept, of a function f, right? If c has an even multiplicity, the graph will bounce off the x-intercepts. More importantly, though, the signs do not change. By signs, I mean positive or negative. If c has an odd multiplicity, the graph will go through. The x-intercept. Or more importantly, the signs do change. And what I mean by signs, again, is the positivity or negativity. This will allow us to draw a pretty accurate sketch of a polynomial function really quickly. So there are two things that we need to know or to have down cold in order to do this. We need to know this big idea here, so we need to know this. And we need to know polynomial and behavior, the thing that we did in 5.2. So assuming we have those two guys down cold, this is how I would sketch a polynomial function. Suppose I ask you to sketch f of x equals, I don't know, x minus 1 times x plus 2 to the 4th power times x plus 3. The first thing I need to do is to figure out my end behavior. And to do that, I would need the degree. Now, it's hard to see what the degree is when your function's in factored form. You can really only spot the degree if it's in standard form, which means you'd have to multiply this guy all out. Well, this guy here, that is a pain in the butt to multiply out. I don't want to write him down 4 times and then do, 6, 7, 8 different foiling. So how do we do this? You only really need to look at the leading terms. So the leading term is to multiply the first pieces along with the exponents. This is what I mean. So in the first factor, we have x to the first power. So that's what I'm going to multiply, x to the first power. In the second factor, the leading guy is x to the 4th power. So that's what I'm going to multiply next, times x to the 4th power. And then the third guy here, oh, I did not want to cover him up. Can you guys see through this? Yeah. You have x to the 1st power. So that's what I'm going to multiply next, x to the 1st power. So when you are interested in only the leading term, you really don't have to do all the foiling. You just multiply out the first pieces. So you have x to the 1st times x to the 4th times x to the 1st. That gives us x to the 6. Notice it's even, the degree is even, and the leading coefficient is positive. So I know that my end behavior should be up and up. Next, I have to figure out what my x-intercepts are. Now, I hope it's not hard to see that with an equation like this, my x-intercepts are 1, -2, and -3. But even more important than what the x-intercepts are the multiplicities. Now, the multiplicities in factored form are simply the exponents. So here, I have an exponent of 1, so he has a multiplicity of 1. Here, he has an exponent of 4, so he has a multiplicity of 4. Here, he has an exponent of 1, which is a multiplicity of 1. And I really don't care what the number is. All I care about is if it's even or odd. Now we can go ahead and do a pretty decent sketch. So I'll go ahead and draw sort of a number. Actually, I'll use the ruler here. Draw a quasi-axis. So I have -1, -2, -3, -4, 1, 2, 3. I guess I didn't need all those spaces. And I'm going to go ahead and plot my x-intercepts. -2, -3, +1. And I'll go ahead and put in my end behavior. So my end behavior was up and to the left and up and to the right. So up and to the left and up and to the right. And then all you have to do is connect the points, but understand that at the x-intercepts, you're either going to cut through or bounce off, and that depends on the multiplicity. So let's connect the dots. So we're going to go to -3 first. Well, here's x equals -3. Because it has an odd multiplicity, we're going to cut through the x-intercept. Next, go to the next x-intercept, which means I'm going to have to curl and touch the next intercept at -2. Notice at -2, he has an even multiplicity. So I know he's not going to go through. Instead, he's going to touch and bounce off. And then you go ahead and connect to the next x-intercept. At 1, 1 has an odd multiplicity, so it cuts through, and you finish the picture. There is a pretty okay-ish shape of that polynomial function. So now we know what happens in the middle of this graph. It should have 2 troughs. So that's it. That's how we sketch polynomial functions pretty quickly if you know the x-intercepts and if you know the multiplicities of those x-intercepts. Let's just do one last example really quickly to show you how fast this should take. So suppose I ask you to sketch f of x equals, I don't know, negative 2x plus 1 cubed, x minus 4 to the 7th power, x plus 3 to the 8th power. So the first thing I need to do is figure out my leading term. And to do that, I just multiply the front pieces. So I got a negative here. Actually, I'm going to do this instead. There we go. I got my negative here. I got my 2x with a cube. So 2x with a cube. I have my x with a 7th. X with a 7th power. And I have an x with an 8th power. So that's x with an 8th power. Then you just go ahead and multiply them all out. So we have a negative 8x cubed, x to the 7th, x to the 8th, which is negative 8x to the 18. So knowing the end behavior, you have an even degree, negative leading coefficient. That should be down on both sides. So then I go ahead and find my x-intercepts, which is solving the equation equaling to 0. So we get x equals negative 1/2, x equals 4, x equals negative 3. But what I really care about are his multiplicities, and they're just the exponents. A 3, a 7, an 8. And I really don't care what the numbers are. I care about if it's even or odd. So this is odd. The 7 is odd. The 8 is even. So now we can go ahead and do a pretty okay-ish sketch. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay. So my x-intercepts are negative 1/2, positive 4, and a negative 3. The end behavior we said was down to the left, down to the right. So let's just connect the dots going from left to right. So the first x-intercept I'm going to touch is at negative 3. Negative 3 has an even multiplicity. So I know he's going to bounce off. But then he's going to have to curl back up to touch this x-intercept at negative 1/2. Had an odd multiplicity, so he's going to cut through. But he's going to have to curl back down to touch this x-intercept, which is at 4. 4 has an odd multiplicity, so he's going to cut through. That is an okay-ish sketch of that polynomial function. So what am I going to be grading when I look at these graphs here? Because of course, the question is how low do we go, or how high do we go? Where exactly does this graph curve? Does he curve here? Does the graph curve there. That is more of a pre-calculus, calculus question. I'm not going to be too concerned about that. So I'm going to be looking for two things. Do you have the right end behavior? And do you have the right thing going on at the x-intercepts? So give it a shot. Once you get the hang of this, once you understand what happens at the x-intercepts based upon the multiplicities, it makes graphing polynomials much, much faster than doing an xy table. Have at it.